All right, so I know this video said polarization, but from that last video, I just want to make sure that you understand what happened in Young's double slit experiment, that it's really, there's two wave behaviors going on. And the first is diffraction. That's the spreading out of light. Diffraction makes the second wave behavior possible, which is the interference. So we have one slit that causes the light to diffract, which falls on two slits, which again causes the light to diffract, and we get those two waves from the two slits meeting up with each other. And really, it's just the two slits in that box. It's the first one doesn't matter. Um, so it's the meeting up from those two slits, those waves interact. So diffraction makes interference possible. And again, we know that it's a wave because we see this alternating light and dark pattern like you saw. If it was just spray paint or if it was just a particle, we would see either just a smattering, a smear of light, or two bright lines on the bottom of the box, just like a stencil sort of. But it's that bright, dark, banded pattern that we get that was very similar to the loud, soft pattern with sound. So I wanted you to kind of understand that. The fifth wave behavior is called polarization. And you've probably never heard about this, but you may have seen it before. I say you've never heard about it. You probably have polarized sunglasses, but you just don't know what's going on with those. So I have a polarized lens here, and I'll put it up in front of this one, and you can tell that all that really happened was that it went darker, which is not surprising. I have another one here, same thing, right? So what do you think will happen when I put these two together? So here's one, here's another one. Just gets a little bit darker, right? That's not surprising either. Here's the surprising bit. 1, 2, but when I turn one of them, then we get complete darkness. Let me hold that a little bit better. All right, so again, 1 and 2, but then I'm going to turn one 90 degrees, and it should go away altogether. It's turned 90 degrees now, and it goes away. Let me back it out, right? So, yeah, that'll work. Dark. You can still see things through it. Can you see? Maybe. You can see my, my headphones through it. It's difficult. If you have polarized glasses, I've got tons of these things here because I buy polarized glasses, and then when they break, I keep the lens. Don't throw the lenses away because you can do this with them, and you can wow people. Right? 1, 2, turn it 90 degrees, and we get darkness. All right. So what's going on there? Let's talk about that. Well, I want you to know the definition of polarization. It's that light waves can vibrate in one plane only, and that's important to know because they usually don't vibrate in one plane. I told you about what light waves are and that it's a transverse wave. Well, there's not just one wave. Light coming from the sun is non-polarized, and so it goes in all directions. But it can be polarized, which means we can filter all that stuff out. So here's basically how polarization happens. Imagine that this polarization, this polarized lens is kind of like a filter. Like imagine it like jail bars, sort of. And if we're going to pass a broom through jail bars, it doesn't work like this. It gets in the way. Obviously, if we pass, so if this is a light wave, if the light wave is perpendicular to the filter, it's not going to go through. The only way to get this broom through is to pass it through parallel, and that's pretty obvious. So light is going to behave the same way. If this is a light wave, when the light wave is vibrating parallel to the direction of the filter, it's going to pass through. But if I turn the filter 90 degrees, this light wave simply isn't going to go through because it's a three-dimensional thing. Again, this is a wave behavior. It shows that light isn't simply just a particle flying through space. It's a wave that takes up some space that moves, and as we can see, if the wave is vibrating in a direction that is perpendicular to the filter, it's not going to get through. Now, here's how this works. As I said, light from the sun is not polarized. It's non-polarized. It's vibrating. They vibrate in all directions, and I'll give you a picture that represents that in just a second. So the polarizing filter, which is what I showed you here, only lets one of those vibrations through and it blocks all the others. So here's what happened with the sunglasses just now. This little diagram represents what sunlight is. So again, there's one wave that will be vibrating up and down, but another one that is also going left and right, and then at all angles to each other. So this is representing non-polarized light. These light waves are not vibrating in only one plane. When I send this sunlight through a polarizing filter, which represents the first lens, only one of these gets through, and that's the one that's parallel to the filter for the reasons I showed you a second ago with the broom. So now the light coming through this is polarized, right? It kind of filters everything out. There are polarizing lenses for cameras, and it just makes the image crisper and clearer because you don't have all this noise light on the side. You still get the same image, but it's a lot clearer. Also helps you to see into water as well. If you're going fishing, use polarized glasses. But then if I send this light through a second filter that is oriented perpendicular, now what I've done is I've got polarized light that is vibrating up and down, and I'm trying to send it through a filter that is oriented perpendicular to that. Well, it can't get through for the same reason the broom couldn't get through the jail bars that were oriented the other direction. And what we actually see is that there's no light on the other side. And what's important to know about this is this shows in a really good way that light is not simply a particle. If it was, and we put these two filters together, you'll notice that there are actually physical spaces here for particles to go through. So if light was simply a particle, just a little photon of light traveling in a straight line, we would see light on the other side because it can get through, right? We can get through one direction, but when you go the other direction, that's when something interesting happens. We actually see no light on the other side, which tells us that light is not simply a particle, right? So this seals the deal that light is a wave because it reflects, it refracts, it diffracts, and it does interference, and we get polarization from light. Light can be polarized. In the next video, we're going to look at the particle behaviors of light.